Alrighty then, welcome again and again and again. This is the last part of chapter 16, I believe it is, from your Zumdahl text. Topic is complex ions. Not complicated necessarily, but where some positive, usually metal ion in aqueous solution joins up with some negative species in the water, forming what we call a complex ion. In a sense, it's an acid-base reaction. I think we've kind of seen some of this before. Let's name it. Let's call it a formation constant, a stability constant. The larger the constant is, the more stable it is. The smaller the constant is, the least stable it is. Here are some examples we saw from a previous blah blah blah. Oh yeah, so my KSP for strontium phosphate, 10 to the negative 31. Guess what the formation constant for this would be? If I were to take this ion and mix them together to ask the question, would they like to form strontium phosphate? The answer would be 10 to the positive 31, which is the reciprocal of this. Or even smaller smaller KSP for cobalt hydroxide. Very, very little of it gets into the water. Or if I turn the equation around, I say, what's the formation constant for copper hydroxide from copper and hydroxide? Oh gosh, whatever the reciprocal of that is, like 10 to the positive 43-ish. Another specific example, lead bromide. Slide over a little bit here. Lead bromide aqueous. Lead bromide solid. A little bit of it gets in the water, 10 to the negative 6-ish. So if I turn this equation around, said what's the formation constant for lead bromide forming from lead and bromide, lead ion, bromide ion? Answer, the reciprocal of that number. Or make it even smaller if you'd like. Here's the weird dimercurous mercury 1 plus iodide, solid solubility product to the negative 29, 10 to the negative 29. So take the reciprocal of that to say how likely are these to want to come together to form this, and the answer is a lot, very likely. All right, let's go back to my original slide here. There we go. So let me imagine an iron ion, an aqueous, and a cyanide ion coming together with it. Call it K1 in equilibrium. 3 plus, 1 minus make 2 plus altogether. We call this a complex ion. But let's add another one. And it can do this. And let's add another one. And let's add another one. And let's add another one. You can see where I'm going with this, but you ask yourself, how far can it go? Well, the iron 3 plus ion that we started with likes to have 6, which is twice that number 3, of course. 6 coordination sites around it where ligands, negative tending Lewis bases, attract the positivity of the iron ion. And that's the end of it. And that would be hard to know unless you knew something about the chemistry of iron and complex ion formation. And in any case, each one of these steps has a constant. Probably all of them are larger than 1 because this really does want to form. You may not know that, but I'm telling you now. So the overall constant for the overall, if I were to add all these up, you see this one would cancel with this one, and this one would cancel with this one, and this one cancels this one, and this one cancels this one, and this one cancels this one, and all I have left is 1 iron ion coming together with 6 cyanide ions, and I have an overall constant. You may not remember this, but when adding equilibria equations, the overall constant for the result is the product of those individual equilibria constants. So let's do an experiment. Let's say I had cyanide ion from potassium cyanide at 0.11 molar. That's kind of a large amount. That's kind of fixed. Very, very, very small amount of iron, resulting in a fairly small amount of iron thiocyanate complex. Not thio, my bad. Iron cyanide complex in the water. So I measured it. Although this is the biggest number of any of them. the 0.11 molar cyanide coming from potassium cyanide, small amount of iron, resulting in really what happens is all of this, no matter what there is in the iron ion here, comes together with this to go this way, reducing the 0.11 a little bit, but not very much, and resulting in some formation of the iron cyanide complex. You do the math, you find the constant to be 42, 10 to the positive 42. That's a big constant. Crazy. That means that this complex really, really, really wants to form with a lot of, call it driving force or something. A lot of impetus, a lot of desire if you personify it. Let's look at a couple of others. Here's a silver. I know that most chlorides dissolve in the water except for silver chloride, so I form a precipitation. But then I come along and take that silver chloride and add something else to it. I'm going to add some ammonia to it. Well, if I add enough ammonia, what happens is this ammonia, NH3, drives away that chloride, and this solid is allowed to dissolve back in the water. All my ions are aqueous. I usually try to say it's solid if it's not aqueous. So this goes into the water, this goes into the water, and I in a way, I resolubilize the silver. Interesting. Yeah, here it says 2 ammoniums like to join up with the silver. Like you wouldn't know that, but I'm telling you now. There's a later chapter that practices some more of these ideas. Let me show you a short video clip. It's going to come up. Oh yeah, it is. That's interesting. I wonder if I could pull that up a little bit. See the bottom of it? No, I can't go much smaller. Yeah, let's go for it. Here's the bottom of my test tube. This test tube has silver ions in the water. I'm going to add some chloride. There's the silver chloride precipitation. A white, interesting looking precipitate. It would sink to the bottom if I let it, but I'm not going to let it. I'm going to add some ammonia. So there's some concentrated ammonia water. Let me shake it up a bit. See if I can get it to dissolve. There we go. Now it's dissolving. Okay, let me pause that video so you can believe me right now that redissolved. Let me go back to here. Then to that, I'm going to add some bromide ion. And I guess the bromide ion displaces the amine ammonia from the silver, forcing another solid precipitation. So every time I see a reaction, this is more stable than either of those. And this is more stable than this. And I guess this is more stable than that. So every time I see a reaction, my constant favors going forward, or if I just had a whole bunch of stuff, like Le Chatelier would say, a whole bunch of this stuff would force this reaction this way. Let me see if I can observe that silver bromide precipitation. Here comes some bromide into that mix of soup, that complicated conglomeration. I don't even have to stir it really. There you go. There's silver bromide, slightly different color than silver iodide. And now, what am I going to do next? Oh, now take a thiocyanate ion. So take this silver bromide right here, the precipitate, and add to it something that wants the silver even more. Or in a sense, it wants it more. The constant for this formation is this is more of a driving force than staying together would be. Let's see, where's that? Here we go. Probably I'll have to shake it again. I don't have to shake the precipitates because they form right away. Oh, I don't have to shake that one very much. I'm going to shake it a little bit though. And all of it dissolves. Pause for a second. And the last step on this little video that I have for you is I'll take that complexed ion and add some iodide to it. And I suppose the iodide really, really, really wants the silver and pushes the thiocyanate out of the way, forming another precipitation. Yeah, like I said, this is the last one. Here comes the iodide. I don't know if you can tell in the video, it's a little bit different colored. There's the iodide. It's kind of a slightly yellowish silver iodide. Oh yeah, I can kind of see it. Interesting. Interesting how it sinks to the bottom of the test tube. You can see the swirlies coming around. All right, so what does that mean? Well, let's look at the constants just briefly for silver chloride, silver bromide, silver iodide, the formation constants. If I know the KSP numbers, take the reciprocals, and I get the formation constants. I see that this is a huge formation constant. That's pretty big. That's pretty big as well. But this one is what, 1,000 times bigger than this one, and this one's 1,000 times bigger than this one. So the silver iodide really is really stable. Does not want to dissolve. Another way to say it is I have increased stability or decreased solubility. This does not dissolve at all. Well, it does. I'm lying, not compared to these. This is, 1,000,000 times more than, less soluble than that. Something to think about. One more example. I have time, maybe. Copper ion, very rare 1 plus copper ion, X minus, constant. It's 100. So this really wants to form. I got 100 times more of this than the product of those two. All these are aqueous, even if they're uncharged in this case. This constant is 10,000. So if I took this and took this, it'd form 10,000 times more of this as compared to the product of those two. This constant is 1,000. So again, I take this one and this one, and each time I'm adding another X minus, probably a chlorine or a chloride or a fluoride or a bromide, take this one and go here, take this one and go here, add those all up and you get this one. The overall constant is indeed this one times this one times this one, 4, 5, 6, 7, 8, 9, 10 to the 9th. So a question, take that and run with it. What if I took 50 milliliters of 10 molar X minus? That must be a very saturated halide salt of some kind. That's 500 millimoles or 0.5 moles, half a mole of this stuff. And let's also take a small amount of copper ion. So a small amount of this is going to react totally one way with this in the beginning of my thought to make this. But then it won't just stay like that. We know the story. I say, I take all this and take it with this is 500 minus 0.1 is 499.9. So that's very, very close to 500 anyway. To estimate, I just rounded it off. Made 0.1 millimoles of this complex. So if I wanted to know the concentration of this complex in this original mixture, really all you need to do in this sense, in this stage, is consider that overall constant, 10 to the 9th. So I'm thinking I have a lot of this, relatively speaking, a fairly large constant amount of this. But then that stuff turns around and goes right back around and makes an equilibrium. I also said since there's so much X minus from that salt, half a molar. No, that's not right. It's in 100 milliliters, so that would be 5 molar, I think, unless I'm wrong. Yeah, 5 molar. So I've got a whole bunch of this pretty much fixed. I've got a little bit of this, but that's pretty much fixed as well. But it will turn around and go back this way a little bit. But that constant is so large that I'm going to have very little of the backwards to go create any more copper ion in the water. But maybe a little bit. Next slide. What does that all come out to? Oh, I rewrote it backwards. I said, let me write not 10 to the 9th, but 10 to the negative 9, thinking about a KSP, or not technically a solubility product, but close enough, since this is decomposing, dissociating into those two. And I know this is pretty much just about fixed at 5, and don't forget to cube that. That's an unknown, and that's a small amount, but still fairly fixed. I could go 0.001 minus 0.000008. It's pretty small. I'm running out of time. Rats. You guys aren't disappointed. Anyways, let's see. Then the next step of the stage could be to say, what's the concentration of this species? Well, if you go back to the other equation, the third equation in the stepwise addition, and you put the numbers in, you know if this is from above, this is from above, I can solve for this intermediate species as well. It's all very tricky. You got to think about it. Feel free to ask questions when I see you next, or ask your TA. Thanks again for watching, guys. Seriously.